Let's hand over to Tomislav Šimunić and Enrico Maria Talarico, vehicle dynamic engineers at Bugatti Rimac. Tomislav and Enrico will talk about the importance of driving simulators and XIL solutions in developing the performance of electric hypercars, using the Bugatti Rimac as an example. It will be emphasized that the record-breaking technology of the Rimac Nevera was developed with the help of driving simulators.
Hello everybody. So today I will talk about the development of our electric hypercar Rimac Nevera together with my colleague Enrico, who will give you a couple of examples of performance engineering, what we used in the development of this vehicle. Yesterday when we were approaching this event, we had very hot weather and then suddenly happened storm. And this is exactly the name of the storm we use in Croatia, and we call that Nevera. And this is where the name of the vehicle come from. It's not related to the Spanish language. Okay, I will start with the history of the company introduction. So everything started as a garage project back in 2010 when Mate Rimac, company CEO and founder, decided to convert old electric BMW E30 on electric powertrain. To show the benefits of electric powertrain compared to combustion engines. Today, Rimac Group is more than 2,000 people on 8 different locations around the world, with the headquarters in Croatia, not less than 3 hours from here. Developing technology, we passed through 3 different stages. The first one was from 2011 to 2015, where we were focused on prototype projects for big OEMs. One I see here was colleagues from Idiada. One of them was Volare in 2013. And focus was on the survival of the company. From 2016 to 2020, we were focused on growing, and we did low-volume projects for big OEMs. One of them is like a battery package for Aston Martin Valkyrie and Koenigsegg Regera. And today, from 2020, we are focused on high-volume projects, industrialization, and automatization. In the parallel with the development of the technology, we also developed 2 hypercars in case of Rimac brand. The first one, Concept 1, was developing back in 2011. And it was developed by a very small team. Just 8 cars were built with single type approval homologation. And from 2017, we started developing of Rimac Nevera. Rimac Nevera is completely another level of the development compared to Rimac Concept 1, with production volumes of 150 cars and still a relatively small engineering team behind this project. And it is a globally homologated car. With this car, we wanted to set up new benchmark in the performance. And before a couple of weeks, we break in one day 22 records in the acceleration and braking for the production cars on the proving ground Papenburg in Germany. And yeah, I can mention that this was with production tires and no special surface preparation. In 2011, big milestone happened for the company when Bugatti automobiles from France with Rimac brand merged in one company called Bugatti Rimac, still with the headquarters in Croatia. Today, Bugatti Rimac is responsible for the development of new generation of Bugatti and Rimac brand vehicles, combining 110 years history and heritage of Bugatti brand with state-of-the-art and leader in electric powertrain technology from Rimac brand. And here is the company structure. So today, Bugatti Rimac is company 45% owned by Porsche Group, 55% owned by Rimac Group. And Rimac Technology, it's 100% owned by Rimac Group. Now I will talk a little bit about the vehicle dynamics process. So before a couple of years, we implemented well-known V-shape development process. So we are starting from the benchmarking, target settings, then going on concept definition. We are cascading the targets on systems and the subsystems, like it's shown here in the example of the suspension. But we are doing that for every subsystem, also like torque vectoring, tires, the same approach. And then we are going, of course, for the prototype components, system bench testing, and on the end, vehicle prototype testing. Of course, we are bridging this gap using driving simulators. And we have one in the company, compact one, but we are also using quite often here in Udine DIM 400. And this is also reflecting on very extensive time in the timing of program of using the driving simulators compared to 15 degrees of freedom models and also multi-body simulations. Since we didn't have previous models and history, we were developing together with the product also methodology. And for us, it was very important to have a clear definition of the targets, especially in vehicle dynamics. So we're starting from, usually from product definition, high level. And this is a couple of examples we had for Nevera. Then we are deep diving in the vehicle dynamics targets. For example, here is a couple of examples we have for the vehicle handling. How we are doing that? We usually select a couple of benchmark vehicles, measure them, and then together with all people who are relevant for the product definition, like board of members, sales, marketing, various people, we try to position our new product in comparison with this car for each of these attributes. Usually we are organizing driving event, and then vehicle dynamics engineer sit with these people in the car and try to point out on which maneuvers and which reaction of the car they need to concentrate to get the feedback from them. And then, of course, our job as vehicle dynamics to translate this subjective evaluation to objective numbers. And on the end, we have the list of the targets for the new vehicle. And this is relatively straightforward for like standard maneuvers, the steady state and frequency response. But then for our car, we also had some high-level targets. And from the beginning of the project was important for Rimac Nevera that this ability for drift. And this came directly from Mate, company CEO, because if we come back on the beginning of story, he was doing drift competition with old BMW. And we wanted to build a car which is not have artificial feeling during the drift. We wanted to have like natural. And we identify realignment as one of very important vehicle dynamics characteristic of passive car to drift. Usually what we do on the big platform on 120 kilometers per hour, step steer, limit step steer, and then after till car didn't settle, so with building up side slip angle, we are releasing the steering wheel. And then we are monitoring what is happening with the car. And then you have different cars. Here is, for example, in the purple one, you can see very snappy car, which builds quite a lot of side slip angle and on the end spin. Of course, we didn't want that. On the other side, you have the cars with very strong rear axle, which are not building a lot of, and has very low overshoot, like the red car in this example. And then you have something between. And usually we identify which cars are good and try to improve. And from that, we are getting the list of targets, for example, for this specific attribute, which is not part of steady state and frequency response. Once we have the list of the targets, we are deep dive in the development. Usually, we start everything with the virtual development with classic 15 degrees of freedom models. And then, if you don't reaching these targets, of course, in the beginning, it's not possible that you reach everything. We are doing sensitivity on some specific characteristic, for example, suspension. And you can see here, it's lateral toe compliance of rear axle, and how it's influencing on this reaction of the car and during realignment. Of course, when you increase lateral toe compliance, you are reducing the overshoot in the returning of steering wheel, but also the side slip angle. But yeah, also then we are doing. It is also changing the phase between these two, and sometimes just looking at these numbers, it's not easy to find and to conclude what is the best one. And this is the beauty of using driving simulators. Then we are putting the driver in the loop and have sometimes confirmed this characteristic we found previously in the offline simulations. And then, of course, if all the targets we reach, or we need to, of course, not change it, if everything is confirmed, we can go on with the physical development of the components, systems, and subsystems. And the similar approach is for every other, like torque vectoring or any other system in the car. Okay, now Enrico will show you a little bit about the performance engineering examples.
So, thank you. Good afternoon. So, I will address some techniques and what we did, we are doing with our record breaking car Nevera, and what we for sure are doing and we are gonna do for our future developments. So I will present you some test cases. So the first test case regards an energy management process in a Nürburgring Nordschleife circuit using software, combining software and driver in the loop for sure. So what's the goal? We wanted to for sure optimize performance, but as well also monitor and optimize brake and battery life. And for sure, this was also inside of preparing the vehicle before the testing and also the drivers before the testing. So what we can see here, we did some tests, some strategies. You can see them by colors for sure. So with respect to a certain baseline, we can see, for example, on the screen, like a blue strategy that reduces the load on the brakes, but at the end of the lap, we are gonna triggering the rating of the battery as well. So for sure, this also in turn is a loss and an overload on the battery, but also a loss in performance, and as you can see from the lap time as well. Then we have, for example, the white strategy, so another strategy which saves much more than the previous one, the brake, saves a lot also the battery, as you can see, as you can witness from the temperature, but it leads to a non-neglectable loss of time during the lap, and this for sure is not ideal. So at the end, it's all a matter of finding that sweet spot that is the green strategy in that case, in which we were capable to save brakes, not arrive at the rating, but also as well gain some lap time and for sure not lose that. And so at the end, after this simulator session, it was very useful to choose one of these strategies and go for it in the testing. So let's skip to the second test case. So this test case regards one of the other powerful weapons of our Nevera, that is the four-wheel independent toll vector system. In that case, we focused on a particular section of Nordschleife again, that is the one from Bergweg to Kesselken, so it is quite a mid-high speed section. And for sure, we tuned the component, the 12 vectoring, in order to improve the performance of the car in that particular context. So this is what we can see here from telemetry. So we can see that, of course, for sure the tuned car behavior is the one in blue with respect to the red, that is the baseline. We can see how we are introducing a toe vectoring yaw moment in the vehicle, and by this we are agilizing the vehicle when needed, so improving the turnability of the car, but also stabilizing it when some snaps occurs. So this in turn leads to a change on yaw rate and steering wheel angle, and by thus understeer. And this is what at the end is witnessed by this diagram in the center. So for sure the gain lap time in that section is half a second, but at the end what we can observe that the toe vectoring, so the yaw moment introduced by the toe vectoring, is mainly working to decrease the understeer of the vehicle. So what we are observing is that when the TV is acting for agility, we have a relative reduction of understeer. And this is what was the main goal in that section. Last test case, we are again at Nürburgring. So last test case regards data analysis inside especially for driver coaching. So again, we have some telemetry data. So what I want to point out in this slide is that, first of all, if we analyze the data as a whole in a circuit like Nürburgring, 22 kilometers long, it's a bit difficult to find from conventional speed, steering wheel angle, throttle, and brake, very specific attributes and very specific differences. So in this case, we are analyzing not two different vehicle setups, but two drivers on the same vehicle setup. So what we can see here from telemetry is just macro differences. So for example, we can spot the driver 2, for instance, the blue one is pushing a little bit more on the brake. There are some snaps. So we can capture high-level differences. For sure, then dividing the circuit into sectors helps a lot to pinpoint what are the main topics and the main stages of the circuit in which there is the difference between the driver. So in this case, we can see that the main difference between these two drivers is in sector 7, and by need we can highlight sector 7, do a more deeper analysis of what's happening in sector 7, and so in this case, sector 7 that goes from Klosterl to Hoheacht, we can see that driver 1, for instance, is going, let's say, too early on the throttle, has some snap, goes wide in the trajectory and loses half a second. Then after carousel heading to Hoheacht, driver 2 is braking in a harder way than driver 1, so keeps tighter to the apex and then goes full throttle. And this is half a second. But this approach is, again, okay, it's very useful to pinpoint very specific parts of the circuit, but is not immediate to spot differences between the two drivers or between two different setups. So for this reason, we think that it is useful to analyze also, to build some KPIs and analyze things also by some metrics. So I guess you saw many GG diagrams, for sure. So what we did is divide, in that case, the GG diagram into different driving regions. This helps a lot because we can distinguish between pure lateral, for instance, pure longitudinal as well, but also combined load behavior, so braking turn and power in turn. And this helps us to build driving regions, but also some KPIs, interesting KPIs, I would say. So in this case, we can spot, for example, so using these regions, we can address what is the distribution of driving regions operated by the two drivers. And in this case, we can spot that the percentage of time driver 2 is spending in pure lateral is higher than driver 1. So there is like driver 2 prefers to use more the lateral potential in the car with respect to the trail braking of driver 1. So at the end, you can see also this kind of difference by the pedals usage. So driver 2, again, harder than brake, then pure lateral and turn in. But another interesting point is that driver 2 uses a higher, reaches higher percentage of side slip angle. And so this is an index of how he's pushing the car to the limit. And this is also witnessed by what? Some interesting KPIs on the steering wheel angle. So average steering wheel angle is the same by the two drivers. So the, let's say, understeer feeling is the same. But driver 2, as you can see, is using higher energy in the steering wheel angle. We see that the steering wheel angle speed, root mean square, is much higher than driver 1. And also, building, let's say, an index which measures the corrections on the steering wheel, we can see that it's acting much more on the steering wheel. So, at the end, this helped a lot to prepare the two drivers, and especially for driver 1, understand where he was losing time with respect to driver 2, and also adapt its driving style. So, I hope you enjoyed it. I will leave the floor to Tomislav.
Yeah. We're a little bit out of time. Okay, when we are doing the project, and vehicle dynamics engineer often in the beginning and in the middle of the project asks yourself, is this target are set up properly? Is it everything like in product definition people wants? And this is, again, nice to have driving simulator, because very early in the project you can put and like confirm these targets with the driver in the loop. But still, we are not selling virtual cars, we are selling real cars. So the first proper, let's say, confirmation comes when you have prototype. And when you put people in the prototype, so the board of members, and they see, and if they are happy, you're also happy. But the last one, confirmation in the program, which is like 5 years, we like that a lot, is coming also from the journalist. And yeah, here I put just for Nevera some impressions. So we had luck that we received very, very good reviews from all the journalists around the world. And for the end of this presentation, I will just leave one of my favorite reviews, a quick video, which is directly related to what we talked today, ability for the drift and realignment.
And it doesn't stop there. In case all that straight line fun wears off, Rimac says they've been to town on the handling too. Each wheel's motor is independently controlled, so the way the Nevera drives can be transformed at the flick of a switch. A switch that includes drift mode.
Dear me! This is a drift beast like I've never been before. It's so easy. It's just wind the lock on, bit of throttle. Oh, they're clever. They're clever, and it's fun. It's fun and it's silly. This car slides. It feels fantastic when it's moving around. I know it doesn't have the noise, but when you've got this performance, I'm starting to wonder if you care.
Of course, we have seen this sort of digital drifting before. In recent years, it's become pretty much the standard party mode for performance cars all over the market. But this being Rimac, in the Nevera, there's also an after party. 4-wheel drive, no traction control, all wheels spinning.
Here we go. Good God. What is going on in this car? We just did a tire in one skid. That's just ridiculous. Mr. Rimac, you are my kind of lunatic. Yes, you are.
Okay, that was it.